thank you to the organizers for inviting me and to the Fields Institute for supporting this wonderful workshop. We're going to talk about crossing number. So there's a lot of crossing numbers. I was just at a workshop last month where I think we discussed at least 25. So I want to make very clear what sort of crossing number I'm talking about, which is the standard crossing number. So we can all be happy about that. We minimize the number of crossings across all good drawings, where good drawing doesn't allow any two edges to cross more than once, no edge can cross itself, and if we don't allow more than two edges to cross in one interior point, we just perturb them a little bit. So it's exactly what you want it to be. But I'm talking about sort of finding minimal guys, and so for k-crossing critical graphs, there's this question of, what's minimal? What sort of structure can we discard or ignore? When we talk about excluded minors for embeddability, there's this question of topological minor, right? We suppress vertices of degree 2. And so we have something very similar in this case where really if we have just a vertex that has two neighbors, we sort of treat it like a degree 2 vertex in a topological minor and just suppress one side of that. So we would ignore a structure like this with this doubled path and sort of minimize down to this graph here. Now, Bocol, Operovsky, Richter, and Salazar gave a near complete characterization of two crossing critical graphs on the plane. In a few stages, they characterized the three connected graphs that are two crossing critical that contain a topological minor, isomorphic to the Möbius ladder on 10 vertices. The three connected graphs that don't have a V8 topological minor, and they describe how to piece together these graphs of higher connectivity to find the two crossing critical graphs that are one connected, disconnected, and two connected. Now you see there's a little bit of a gap there, missing V8 to containing V10, but they did give a bound for the order of graphs in that gap. So what family that I'm interested in is extending what they have for graphs that contain the V10 minor up to higher surfaces, because that family has a really nice structure. And I'll give the result in a moment, but just sort of a template for the types of graphs we're talking about are in this belt of tiles where this tile is filled with some sort of picture here, and then there's a special edge or two that I'll show you on the next slide. This example is mostly just here for notation. So we have a tile joined to a tile that's inverted. Both the left and right sides are reversed, and then we just keep alternating. They've got an odd belt there, and give a little half twist to the very last tile, and the circle here is that's glued back around to the front. So it's, think of Möbius ladder, and we just shove a bunch of stuff in those quadrangles. There are two frames that contain 13 pictures, and these are our frames at the top. So those arrows at the top, we're taking the frame here once we slide a picture inside and just flip it upside down. And you'll see that although not all the graphs are simple, there's plenty of graphs that we can build in this family that are simple. So if you're really averse to multiple edges, there's still a family out there for you. So here's an example of one of their two drawing of one of the graphs that contains V10 as a minor that's two crossing critical. We've drawn it here with 1, 2 crossings, and this guy has 5 tiles. The last tile's twisted and comes around, so it's perhaps a little difficult to see that it's exactly that picture. And here's the result, right? All those 3 connected 2 crossing critical graphs on the plane, if they contain a topological minor of V10, they're going to be in that family of circular tile joins. And so I wanted to look at higher surfaces, in particular non-orientable surfaces, and of course this twist at the end is no fun at all if you have a cross cap, because, well, now we can just embed willy-nilly. So what I did instead was to say, all right, well, instead of having a Möbius ladder, let's take a circular ladder. So we're going to need an even number of tiles. And add this special vertex who has neighbors in the sort of 2 rims on that circular ladder. Think of this guy as a hub vertex. And because I'm looking at 2 crossing critical graphs, it turned out that he wanted to have 3 neighbors in each of those rims. So this is don't think of this as living somewhere on a projective plane, except in as much as the vertex V exists on the top and the bottom. And so it's this alternating tile, upside down tile that I want you to see. There's an even number of tiles, and then to build a family for the projective plane, without the twist, that means that this vertex is going to be identified with the top left, and this vertex on the bottom right will be identified with the bottom left vertex there. And so we fill our tiles in exactly the same way, and these spring edges here, if you remember the frames, there's either no edge at all, so the two vertices here are identified, or that's a doubled edge. And so you can see perhaps that if I reverse the order of these two, there's that two crossings right there, and then we could slap it on the projective plane and see crossing number 2. And it turns out that all the graphs that I construct in this way, this family script T plus, are all two crossing critical on the projective plane, except for maybe a couple of pathological cases where n is very, very small. But these graphs are two crossing critical on the projective plane. And so what happened? Right? I'm not going to bore you with the details of proof, but what happened is that twist that occurred at the end for the plane, I let the cross cap do it, let the boundary of the projective plane handle that twist. And then so that we can't just nicely embed, I added a vertex with 3 neighbors on each of those 2 sort of boundary cycles. And the 3 neighbors are sort of magical because this one edge can't sort of pathologically twist around. He has to cross 2 of the neighbors. I can't just sort of rearrange things. So the thing that actually feels kind of limiting in moving forward is that when we draw a graph in this family, it's pretty direct to find a forbidden minor for the projective plane, which is great for the projective plane because we know what those are. On higher surfaces, of course, we don't have a characterization of forbidden minors. But essentially, the proof goes very much the same as the plane, which is to say I find this forbidden minor, and I do my very, very best to one-draw that forbidden minor, because if I have 2 crossings, I'm already finished, for the crossing number being at least 2. And then I try to fill in the rest of the tiles, and it turns out that I end up having to have one tile that's just twisted. And so we know from the planar result what sorts of pictures should live in that tile. Now, I said that it was that forbidden minor for the projective plane that really guided knowing that the crossing number was at least 2, and criticality follows pretty similarly. For higher genus non-orientable surfaces, there's a cheap trick. Things aren't connected, but we take the tile belts from the plane and we add 1 for each additional cross cap after the first, plus this 1 graph from the projective plane family. And those graphs are 2 crossing critical on the Klein bottle and 3 cross caps and so forth. And obviously the immediate goal is to kick up the connectivity to, even connected, but 2 or 3 connected would be really nice place to get to see how this one particular family extends to all these higher surfaces. And then for orientable surfaces, I've recently been looking at the torus, and this is one of the graphs from the plane, one of these tile belts. And it turns out that if we take these 2 vertices at the edge of a tile and we identify them in a string, so I'll just take another tile belt from the plane and mark those same 2 vertices, and we'll just glue them together along those two vertices. We get a 2 crossing critical graph for the torus. And if I keep doing this, I add 1 more of these tile belts with a new cleavage unit for each handle, that we get a 2 crossing critical graph for an orientable surface of whatever genus you please. And the barrier to 3 connectivity is exactly the genus is the number of cleavage units we have. And that's all I wanted to say, so thank you.
Okay, thank you. Are there any questions? Over here.
So in your picture of the hub vertices, does it actually matter if you had it symmetrically drawn where it's going to 3? Yeah, that one. Does it matter if the inside rim and outside rim, those three edges share a tile? Like here, none of them share tiles?
Here, none of them share a tile. That I know everything about. So there's three orientations, right? They alternate, they almost alternate, and then they're completely offset up to sharing a tile. So I can think of a couple tiles in a row as being a tile. And so on the same sort of minimal tile, the answer is I don't know all the cases yet. And then if they're completely offset, there's a little bit that needs to be resolved. So there's a little bit of hand waving to hide from you the symmetry, but you caught me. So I think the answer is no, it doesn't matter, but I'm not willing to just say that because I haven't verified.
Any other questions? So I was actually just wondering, do you think that's, I mean, you've got this class of obstructions, do you think it's close to, do you think all obstructions are going to look a bit like this, the projective plane?
Short answer is no. So there's
like for an infinite class, like a finitely many plus thing.
right,
like
that contain some favorite minor, topological minor. Probably not, which is a little sad because there is this result of Clineni and Salazar. They have a family of two crossing critical graphs on the projective plane that are very similar. They don't use any of the exact same tiles, but they have this one vertex, like my hub vertex, that has a really high degree. So it's got, I think, 6K, where K is the number of tiles. Maybe if we have some boundedness on degree, if we don't allow some pathologically high degree vertex, then in that case, maybe. But because they've got this family, it seems to be that there's more hiding there.